I'm here to promote the store collect object as a useful primitive for programming distributed systems that experience ongoing churn. This is joint work with Hagit, Attiya, Sweta, Kumari, and Archit, Somani. We're considering distributed systems in which nodes can continually enter and leave, a behavior that we call churn. When they're in the system, the nodes communicate via asynchronous message passing and are subject to crash failures. This model is motivated by peer-to-peer, mobile, and sensor networks. The key feature is that the churn never stops, although the rate of churn is always bounded. Programming in such churn-prone systems is tricky, as you have to keep track of who is in the system and deal with low-level message passing. By analogy with techniques used in static systems, we'd like to encapsulate the messiness with some kind of shared objects. Now programmers can use familiar data structures and not worry about tracking the system composition. But which objects should we provide? We propose the store collect object, first introduced by Attiya et al., as a strong candidate. Each node can store a value and collect a set of recently stored values. In this diagram, nodes P and Q perform some stores. This collect invoked by node R must return for each node a value from the most recent preceding store or from an overlapping store. The collect by node S has the same constraints. Notice that this example is not linearizable since R sees the P's old value and Q's new value, while S sees P's new value and Q's old value. Finally, this collect by node T must return a value for each node that is at least as recent as that returned by any preceding collect. We've designed a simple and efficient implementation of a shared store collect object that hides the complexity of the churn and the crashes. On top of this object, we show how to implement a suite of useful data structures, including max registers, abort flags, sets, and atomic snapshots. Our atomic snapshot algorithm is also simple and efficient. Atomic snapshots can be used to solve many problems such as group membership and mutual exclusion. In our paper, we show how it is trivial to implement a generalized lattice agreement object using an atomic snapshot object. The generalized lattice agreement, in turn, can be used to implement other objects, notably conflict-free replicated data types. The brown boxes indicate algorithms that are given in our paper. All these implementations inherit the churn resilience and fault tolerance from our store collect implementation. Next, I'll introduce our store collect algorithm. We track the system composition using the same mechanism that's used to implement a churn-tolerant register in the paper by Attiya et al. The store and collect operations are executed similarly to the reads and writes in the register algorithm. The key new aspect is that each node keeps a local view, which is a set of node value sequence number triples. Views are merged by taking the value for each node with the largest sequence number. And I'd like to briefly mention that our correctness proof is much simpler than that in the original paper. When node P invokes a store for value V, it gets a new sequence number. It merges the new data into its local view. It calculates a threshold value T and broadcasts a store message that contains its local view. When another node receives the store message, it merges the received view into its local view and broadcasts a store echo message. When a node receives a store echo message, it merges the received view into its local view. If the recipient of P's store message has already joined the system so that it has sufficiently up-to-date information to participate, it sends back an acknowledgement to P. Once P receives enough acknowledgements, remember our threshold T, it completes the store operation. When node P invokes a collect operation, it first calculates the threshold T and broadcasts a collect query message. Each recipient of a collect query responds with an acknowledgement that it has already joined. When P gets back enough acknowledgements, it calls the store algorithm with its current value as the argument. And then it returns its local view once the store finishes. Now that we have a churn-tolerant algorithm for store collect, I'll explain how we use it to implement an atomic snapshot. With an atomic snapshot object, each node can update a value and scan the set of latest updated values. The operations must appear to occur instantaneously. In other words, there must be a legal sequence of the operations that respects the order of non-overlapping operations. This is similar to a store-collect object, but stronger. Here's a simple first cut at an algorithm that uses a shared store-collect object. For an update, simply store the value together with a new sequence number. For a scan, keep executing collect until getting 2 identical views in a row. If we get the same view twice, then no changes have occurred in between, and it is safe to return that view. This is called a direct scan. However, it's possible that the scan will not terminate. Following the classic algorithm by Hagit et al., we can make updates help scans terminate. Each update first does a scan, called an embedded scan, and then includes the result of the scan in its store. The scan applies some rule to determine if it can borrow one of the scan views that appear in the result of its latest collect. P can borrow the scan view from Q's entry in the latest collected view if Q's embedded scan is enclosed within P's current scan. The mechanism that we use to check for this condition is scan sequence numbers, which I'll now illustrate. At the beginning of P's scan, it stores its scan sequence number and then does that series of collects. At the beginning of Q's update, it does a collect, which obtains P's scan sequence number. Then Q does its embedded scan and stores its new value, the scan sequence numbers that it collected initially, and the view from its embedded scan. Once P collects this information from Q, P can safely borrow the view that came from Q's embedded scan. Our atomic snapshot algorithm ensures linearizability. However, the proof technique of the original algorithm doesn't work for us, as it relied on linearizable building blocks, but our building block is not linearizable. Instead, we define an explicit ordering of all the updates and scans, including the embedded scans, and show that the ordering satisfies the necessary properties. A key step is showing that all direct scans return comparable views so that they can be ordered according to this comparability. The store-collect properties then ensure that the order of non-overlapping direct scans is preserved in our ordering. We then have additional rules for how to order the borrowed scans and the updates and to put them in the right places. Our atomic snapshot algorithm is efficient since the store-collect lets us collect values in parallel. We show that each scan does at most n collects, where n is the number of nodes in the system when the scan begins. If n is the number of nodes in the system when an update begins, our churn assumption ensures that when the update's embedded scan begins, there are O of n nodes in the system. Thus, each operation takes O of n message round trips, since each store takes 1 round trip and each collect takes 2 round trips. For more information, please attend the live PODC session on Monday, August 3rd, starting at 16:45 CEST, which is 10:45 a.m. Eastern Time. Here's a link to the full paper, and also you can email me any questions that you have. Thank you.